Well, here's my second Gauss's law video that deals with how to derive equations for electric fields. The first one, probably the most common one that you use, is a sphere. I went through a lot more detail on this, or on that one, so I'm going to try to speed this one up by not doing all of the explanation that goes with it. Something I'm going to do on this one is to do a drawing by hand, because my students tell me that sometimes they have trouble actually drawing the diagram that goes with the derivation. But when I use these pre-made diagrams in my screencast, that it's a little hard for them to kind of picture how to draw it themselves. So we have a long line of charge, and so I would just usually draw something like this, and try not to draw something that looks like it starts or ends anywhere, and put a little charge on it. So maybe some positive charge. It really doesn't matter what color you use, but we could put a few positive charges here. And then anytime you're going to use Gauss's law, you're going to need a Gaussian surface that matches the symmetry of the electric field. This was addressed a lot in the opening section of chapter 28 in Dr. Knight's book. And the line of charge has what we call cylindrical symmetry. So you draw a cylinder, Gaussian cylinder, and all my Gaussian surfaces I draw dashed, because those aren't real things like the wire and the charge. These are just little tools that we use as we derive things. So can you picture that line of charge now piercing right through the middle along the axis of that cylinder? And our cylinder needs to have the radius equal to wherever we want to find the value of the field. So perhaps somebody asked you for the field right there at some distance. Let's just label that D. And so that's what we'll call D. That's the radius of our cylinder, and we're going to have a dimension that we call the length, and that'll be how long we draw the cylinder. There's no right or wrong length for the cylinder. It's not infinitely long like the line is, though. And so now we're ready to actually employ Gauss's law. So I usually suggest writing Gauss's law in this form. This is how you'll see it on the AP reference sheet. It takes different forms, but I like to start with that. And then the left side is always kind of treated the same way. You say, all right, I'm looking for some electric field measurement. And you know, for a positive charge, we're going to have this outward electric field. So maybe I'll draw one of these field lines that would radiate out like that. And the reasoning says, well, the field, when it pierces that Gaussian cylinder, should be the same at any distance away. So no matter where we are on the wall of that cylinder, you've got to have the same measure of the electric field. So that means it's not really part of the integral, it's just a number. So we write E, and then you say, okay, how much area is that field piercing through? Well, notice that the end caps of the Gaussian cylinder are not being pierced by the field lines at all. They're just skimming right by it. So those don't contribute anything to the flux. But the area of the wall is completely pierced by this outward field. So what is the area of the wall of a cylinder? This you would just have to know, a little geometry. It's 2 pi times the radius, d, times the length of the cylinder, 2 pi dl. Okay. What do we have on the right side? We have Q in. That means the amount of charge that's inside the Gaussian shape that we drew. Well, how much is that? You know, it's an infinitely long line, so it's not like we can say there's a certain amount of charge on the line. But with lines of charge, we introduce a quantity known as the charge density lambda. So you will see that in a problem, and every source I've seen uses lambda the same way. The amount of charge per meter. So that means inside the cylinder, depending on how many meters that is, the amount of charge will just be lambda times the length of the cylinder. So that takes the place of the charge that's inside, and then we put all that over epsilon sub naught. Now notice what has to happen here. You have to be able to cancel L, because that is not going to be in our final expression for the electric field. But when we algebrate for E, using a slightly thicker pen, we're going to get I'm going to write it this way, lambda over 2 pi epsilon sub naught d. This can also be written, if you like this version better, 2k times lambda over d. So either one of those is fine, depending on which electrostatic constant you prefer to use. So that is the measure of an electric field some distance d away from a very long line of charge. And that's the same expression that is derived by using calculus back in the previous chapter, kind of a much longer and seems harder process. But you do get the same result without any calculus at all. Really, the hardest thing we did there was a little geometry and just understanding how Gauss's law is used. So there's the electric field due to a line of charge as derived from Gauss's law.